Welcome to Unit 7. In this unit, we're going to look at renewable energy sources. We're going to begin by looking at solar energy, but also starting with a discussion of what it means to be renewable. Strictly speaking, renewable means you have to be capable of replacement through regeneration, growth, reproduction. Biofuels certainly qualify. Colloquially, we mean something that is not depleted by human use, in which case solar, wind, hydroelectric, geothermal, and tidal energy sources come into play as well. Who's suitable for renewables? To be suitable for wind energy, you have to have wind. Not everywhere is windy as others. North America and Europe seem to be the best, judging by the size of the circle. For biomass, you have to have a lot of plants. Look at the big dot in South America due to the Amazon. But in general, everywhere is capable of producing energy from biomass. Hydroelectric is going to be really, really good where you have water, but not so good in deserts. So if you consider North America or in South America, you have a lot of rivers, but in Africa, you have a lot of deserts, so not as much hydroelectric powered generation capabilities. Solar, you need sunlight, of course, and everywhere gets a fair bit of sun. Some places are better than others. As you might imagine, along the equator is a good spot, and look at that's where the biggest dots are. In the end, you can trace all of our energy sources back to solar energy, with the exception maybe of nuclear. Think about coal. Coal starts from plants, as does oil, as does natural gas. In order for plants to grow and thrive, they have to take in solar energy. Winds are powered by the sun's light, or energy, if you believe that, I hope. As is the water cycle, so that would contribute to hydroelectric power. Pretty much everything can be traced back to the sun. So what is the sun? It's a gigantic nuclear fusion reactor, meaning it takes hydrogen and makes it into helium. The energy from it is safe, it's constant, it's abundant, so why can't we use it like the plants do? How do the plants use the sun's energy? Well, as you might remember, it's a process called photosynthesis. For photosynthesis, you take in light. The light is trapped by chloroplasts, which are a cell within the plant's leaf. You bring in some water and some carbon dioxide, and those three things combine, and you get out sugar. You get out food, sugar. If you look at the light from the sun, this is a graph of energy emitted from the sun versus wavelength or color. It peaks in the green, but it has a fairly long tail in the infrared, which is good because infrared is actually what heats the planet, and also a tail into the UV. In order to use the energy from the sun, you have to collect it. You then have to convert it into electricity typically, and then you can use it or you can store it. There are several direct solar energy applications. One is electricity generation. However, you can also use the light to heat water directly or heat a space directly. To generate electricity, you need something called a photovoltaic cell. You might know it better as a solar panel or solar cell. It is basically a piece of an electric circuit that converts solar energy into electricity. Here are some pictures of solar panels and their applications. This one is attached to a house. These on top of the poles power the lights in this parking lot. This one powers either a pump or a heater in the watering trough for the cows. To create electricity from a solar cell, you need special materials. Typically used are silicon, cadmium telluride, or copper indium selenide or sulfide. The cell converts solar energy into direct current electricity. All the other electricity generation methods, coal-powered power plants, oil, natural gas, or nuclear, all create alternating current because they heat steam, which turns a turbine. To create the electricity, you need two layers of silicon. You need the N layer, N for negative, which is on top. It's negative because it easily loses electrons, so often it's missing. Let me think about that. It's often missing electrons. So it should be technically positive. I think it's N for negative because it loses the electrons. I got it backwards. The lower layer is the opposite one. It has a hole. It needs electrons, right? And then you have to have some way of getting the electrons from the bottom layer back up to the upper layer. As the electron flows from the top layer to the bottom layer, it creates the electric current that you desire. The nice thing about solar power is that it's at point of use. I can create solar energy at my house. And depending on your usage, you can actually get paid for doing so. So they monitor a meter. If you use energy off of the grid, then you pay for the energy you use. However, if you produce more energy from your solar cells than you actually need, it goes back onto the grid and you get paid for that. The rate, of course, depends on the state in which you live. There are utility scale solar cell farms. This one has 34-foot panels. There are 220 of them. And they produce 6.5 megawatts at peak. Those of you who are actually near Shepherd might have noticed the one that's between Sharpsburg and Hagerstown by the correctional facility in Maryland. Here are some pictures of utility scale solar farms. Here is a parking lot where they've put solar panels on the covers over the parking spaces. This up here, the power of the sun, is a link to a video describing how solar cells work. It is 22 minutes long. Rather than record it and put it into this and clicking on it, I will put this link up on the units as part of the things to watch for the unit. Here is another YouTube video. This one is shorter. Oh, I take it back. This one is 48 minutes long. I will also put a link to this one up on the page and try to give you some guidance for which parts of it are most important for you to watch. The nice thing is that solar power technology, solar PV, is on the rise. Okay, back in 1990, less than 500 megawatts was produced. Today, or today being 2004, so a couple of years ago at this point, 4,000 megawatts were produced total, but only about half of those were connected to the grid. Everything else was privately used. Here is more recent data. As of 2012, 100 gigawatts of solar PV energy was produced, or power was produced.